Hi, everyone. Welcome to another episode of the Common Lisp Study Group. I'm your host, Ron Vadum, with Atlanta Functional Programming. Um, it's been a couple of weeks since we've actually done this. My apologies, last week something came up and I was unable to do the stream at the last minute. So apologies for those of you who are expecting us to continue some of this discussion last week, but sometimes life hits you. Today, we're going to be continuing our discussion of Chapter 8, Symbolic Mathematics, with particularly our study of the simplified maxima system as defined by Dr. Norvig. And last time, if you recall, we talked about the book's implementation and the implementation that's provided in GitHub of the simplifier algorithm that gave you some, basic ideas on at least dealing with some basic uh, mathematics when you're talking about equational simplification. So, for example, in our simplifier algorithm that we encountered in the book in Norvik's code, it looks like the following. We can do basic arithmetic. Okay, naturally. It does respect order of operations here. Okay. Um, Oops, sorry, I have to provide, forgot I have to do, um, 1 second. Simplifier, there we go, and we do 2 plus 3 times 2. We have to put it in parentheses, and what, did I miss something here? 1 second, there is something here that I'm missing here. Let me try this one. 5 times try 5 times 20 plus 7. This this did not actually do the simplification. It's interesting. 1 second. I think there's an issue with my my REPL. Let me try one thing here. Oh, sorry. Apologies. There we go. Abort. Abort. And do restart Lisp. Let's go ahead and reload our okay. Set package being PAIP. Then we need to do requires Macsyma. Okay. Simplifier. Okay, 2 plus 2 plus 2, 5 times 20 plus 3 plus 7. Okay, so now we're able to do that. It follows order of operations. You could see, and in this case, multiplication takes precedence over addition. Um, we have to make sure that the difference between the previous declaration and what I had is unfortunately, right now, our patterns that we're doing to implement this, if you recall, required there to be a space between the symbols in order for our order of operations and simplification rules to recognize the actual pattern or the function or the application of the operator inside of the equation. So if you do not provide a space in between the operator and the two operands, in this case, either the plus between 30 and 7 or the multiplication operator between 5 and 20, what ends up happening is it treats it as a single equation and says that it cannot actually, well, not a single equation, a single term in an equation, and cannot simplify it. Now, a lot of folks who come from other parsers will know that this is pretty trivial. You can actually go ahead and deal with the no spaces rules and extend it. I'm not going to cover that in terms of that. That's actually a pretty simple extension of this piece, just mainly because I think the more interesting aspects of this symbolic mathematics piece is not just the search rules that we've seen and we've encountered to actually perform the simplification, of which today we're going to be covering associativity and commutativity, but at the same time, being able to recognize that the fact that we're able to even do this by doing a simple lookup is quite astounding. It's pretty. It kind of shows that some simple arithmetic operations can be easily implemented by recognizing some of the rules of arithmetic that we've encountered over our years of taking basic mathematics and encoding them in such a way that we could just simply do a lookup and being able to apply those rules. There's other stuff that this current implementation last week well, a couple of weeks ago we covered, mainly some of the basic stuff in terms of if you provide, say, for example, sorry, for some reason, okay, if we do 5 times x and 4 plus 1, sorry, plus 1 times x, you will see that this will get easily simplified to 5 times x times 5 times x. You can also see that if you end up doing this here, oh, sorry, looks like it doesn't actually encounter that rule. The opposite too will actually get simplified correctly, times x. Let's make sure I got that rule correct. X equals, yes, I did. Okay, you'll see that this simplification does not actually do all of the the rules that we've actually encountered. So there's a couple of simplifiers that we need to actually extend here before we move on to commutativity and uh, um, associativity. So let's go ahead and fix that. I think this is actually implemented in, if I'm not mistaken, this is already implemented in the rule that, let's see here, simplified using arithmetic. This is actually encountered already, this simplified by function rules. This is doing the role-based translation. Right, this is doing the role-based translation from the right-hand side. Then it simplifies the binding with the response that we typically have dealt with. We check to see if it's an evaluable expression, and if the expression is evaluated once we see, and by the way, this eval here is what it's doing is it's actually going through um, the expression that was actually provided by to simplify expression, and if it's an expression that has already been in prefix form becomes something that can be evaluated, then it will actually go ahead and evaluate it. Now, what this means is we need to go and look at this evaluable expression function. And this evaluable expression function already checks to see if it's in prefix form. You're dealing with all the basic operands. Um, you're more importantly, not necessarily dealing with um, so so you're dealing with all the basic, sorry, you're dealing with all the basic operators, okay? And you can get that through the exp op function from the structure, because recall that we've defined the structure for the expression as being the same as the pattern matching that we've encountered with the student example. And in the student example, remember there's a left-hand side, a right-hand side, and a operator as indicated by line 20. So what this is actually doing is checking based on the arguments that are passed into the expression um, here later on. Actually, oh, right. Okay. So if you see here, the expression that it's going to get is the um, everything that's the rest of X, right? Because of the fact that in prefix form, the operator is first, and then all the operands are basically, in case of the function call, the arguments that are being passed into the function. Okay. And so what we can do here is we're checking to see if in this case, are we dealing with a proper arithmetic expression that can be evaluated? And in this case, we're checking to see that every number in an expression, every argument in an expression is a number, and we're dealing with either a arithmetic operator, okay, so plus, minus, times, or divide, basic arithmetic operators, or we're dealing with an exponential operator, and that exponential operators, and this is kind of like a look ahead. All right, we're looking ahead and we're checking to see that the second of the arguments of the expression is the actual power to which we're actually going to take if we apply the exponential operator, right? And so what this evaluation does is then we guarantee that this is something that Lisp can understand, and then we go ahead and actually evaluate it. Simplify by function is nothing more than the same idea, but it's actually dealing with the other aspect of the Maxima, which is the symbolic piece. And what that's doing is it's leveraging first. Well, let's first go through the simp function first, which is it's taking the operator and grabbing the underlying simplification function for that operator. And if you look at what this is doing, is this get op, this simp function here is nothing more than what is this? This is actually the get of the symbol and the indicator. So we're actually doing a setf on the function. Oh, okay. So we assign some meta. You could think of this as a function like a tag for the folks who are coming from the Clojure world that essentially is assigned a function pointer on top of the operator that we're looking up. Okay, so when we look at the XP operator, we can actually apply an indicator based on that. I'm just kind of curious, is that a because I don't remember where get is actually defined, commonlist.get, right? This is all part of the set expansion stuff from actually being able to apply an additional property on top of a symbol. So every symbol in Common Lisp has a property list, a plist that you can apply, add some metadata on top of. And in this case, what we've done is or what Dr. Norvig has did is he leverages that metadata on top of the symbol to essentially provide the function pointer associated with the simplification rule on top of this this function itself. Okay, and so what we do is in this simplify by function guy, we grab the simplification function, we grab then the result of it because apply it by calling it on the expression um, if it exists, hence the let star. And if it's not, if it's null, obviously we return nil. Otherwise, we now can further simplify the result. All right, and that's calling the other recursive rule that we actually provided, which is using essentially the lookup tables to actually go in and deal with the actual implementation details related to uh, um, actually simplifying the equations. All right. Um, okay, so ignore some of this stuff. This is all about stuff that we're going to be covering today, which is about integration stuff. Um, but this should be actually dealing with one thing that doesn't seem to be dealing with, which the book supposedly mentions. And when I was reading this earlier, I thought that it was doing it right, but it doesn't look like it's doing it correctly, which is it isn't able to further simplify 5 times x minus 4 plus 1 times x, even though the book mentions that the basic implementation should be able to actually go and simplify that rule. So it looks like we're going to have to actually maybe fix that. Let's see what else from these examples it doesn't actually simplify to. Shall we? Let's see here. Because then this will at least tell us what's supported and what's not supported. Or let me actually go and check this. Maybe I did something. Roswell, local projects, PAIP, Lisp, okay, and Lisp, ST, git check out, Lisp, Macsyma.lisp. Okay, let's go ahead and do this. We may need to recompile our requires Macsyma. Ah, shoot. I'm gonna have to restart my Lisp to get this to actually recompile Macsyma. Do that. Set package. PAP. Now let's require that. Good. Simplifier. Okay. And now let's do this again. Let's try 5 times x minus 4 plus 1 times x. Okay, so it isn't actually still doing it. Okay, we're going to have to fix this simplification rule. Let's see how it did it. Because it should have evaluated this as being 5 times x minus 5 times x. And it's not. So let us see what it's doing. Role-based translator. So we can actually check this expression by doing each of these individually. All right. let's see. Oh, wait. We need to first abort. And let's do simplify by function. Okay. And then here we need to probably in the simplifier, let's make sure that this we follow the simplifier's rules because right, so we need to call simp on the expression and then we need to call simplify by function. Okay, so we do simp on 5 times x minus 4 plus 1 times x. And you know, just to show this off, just to see what this is doing, let's actually first do this piecemeal. Okay, let's see what happens here. Compile with error, legal function call. Right, because it is, we're in Lisp now, so it's going to have to do this. That's what we needed. Okay. Ooh. So simp already minimizes it, right? Because it's simplified doing it. Okay. So we need to first do it even step further than that. Let's do not simp. Let's do infix to prefix this guy just to see what it comes up with. Okay, we first converted everything into this. Then we call simplify on 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 that, but let's call simplify by function first. Okay, on the result of the previous, nothing. Okay, so and that means it must be a proper expression, right? Because it is an expression, we're not dealing with anything special here. There's no internal functions. All right, so now let's see what happens. Let's call okay, so before we do anything, let's call the map car here in simplify. Map car and simplify. And let's take the expression here. This should just give us the minus 5 times 5x times 5x in prefix form, essentially, right? Right. So at this point, we should be able to actually go into simplify expression and then make our judgment that we should be able to um, fix the evaluation. So earlier we must have done okay. So in the previous one, they just had the evaluation expression. Okay, so let's just get rid of this for the time being. see what happens. Oh, right. Let's go ahead and load that. And now let us do this. And let's call simplify, which will ultimately call simplify expression, which we saw in the previous, and see what happens. Okay, there's still this issue that it's unable to actually go in and apply the rules. So that means we need to go and deal with let's go and look at um, the simplifier rules. Okay, so the simplifier actually leverages this rule base, knowledge base that we saw earlier for doing simplification. And the way it does it is probably what's causing this. There might be a bug in there that was accidentally introduced, but we need to handle this correctly in order to handle commutativity correctly. So let's first fix that piece. Um, the way we do that is we need to actually go into here and see what happens when the expression is passed in. Okay. So we need to look at the rule-based translator of this simplified expression. Translator. And we need to go to this. This is, if I remember correctly, what we've already defined in previous, if you remember, in previous episodes, we've covered this. This is actually the same rule-based translator that was used in ELIZA. It was the same one that's used in Student. It's the same one that we've ended up using when we took a look at leveraging GPS too as well. Um, if if anything, when we studied these four systems, right, it should become clear that a lot of the stuff that we're doing is just basically um, trying to leverage a knowledge base to actually go in and run a particular algorithm. And in this case, we're trying to use that to do substitution for us so we could get an expression that we can ultimately evaluate by Lisp using basic Lisp. So each knowledge base rule is just doing a simple, you can think of it like a substitution. Okay. Um, let's see what this guy is leveraging first. And we need to maybe provide the same rule if else stuff that's here. And the rule if it's going to be, actually let's see what happens if I just did it this without doing that. Nothing. Okay, so we're gonna have to actually say rule if EXPLHS because it is an expression. Oh crap. One second, I'm gonna have to say star star because of the fact that I just lost it in the previous history. Okay. Rule then RHS, and then we have our action, which is going to be just like before. We're basically using the simplification rules to take our bounded response, which should be caused by the substitution from the set of bindings to the set of to the actual response itself, and then we're calling simplify on it. Now, if we do that, it looks like it doesn't actually like the rule. So let's see. Okay, so, oh, right. So this AppCar simp rule. Hold on, let me look at this for a second here. This is transforming this all into the simp rule. Simp rule. Here we go. Expanded pattern match abbreviation to the proper format. Okay. So this is just setting up the rules. Let me see how these rules look like once we've done this, because that might give us an indication as to what we're missing here. Oh, okay. That makes sense, because it looks like the problem that we were looking at is because Macsyma did not load Macsyma R, which is our actual rules. What? Two. Hold on one second. Why is this giving me some trouble? Okay, let's try this again. Simplifier, where are you, simplifier? Actually, we could do it this way. Compile it. Oh, it's legal function call again. Right. Done. Okay, so this is actually doing it right now because the rules weren't actually loaded, but everything else seems to have worked without the rules being loaded, which is interesting. It must have been because of the fact that since we're doing basic arithmetic expressions, it would chose to just be able to, because we converted it from infix to from infix to prefix, it should be able to actually be able to simplify that. Okay, so we now are able to do what we expected, which is, so note to self and folks who are watching, in order to actually load this and study this on your free time, you need to actually load. So to play around with Dr. Norvig's stuff, load Macsyma R, not Macsyma, to actually play around with, because Macsyma R actually will load up Macsyma in order for you to actually be able to run the simplifier. Okay. So if we end up doing this, you could see that if we did, let me just show that to you. Okay. Okay, set package requires Macsyma R, which will include all the rules. Now we could do simplifier, because we loaded maxima through maxima r, we get 2 plus 2, good. We get 5 times 20 plus 30 plus 7. You also get 5 times x minus 4 plus 1 times x. We're good. Oh, right, because I did not do this right. This should be 5 times x, 4 plus 1 times x. We get 0. Now, this also handles this sort of situation. If you have f of x plus 0, you will see f of x appropriately, because f of x, that notation there was converted from infix to prefix through the function call infix to prefix, and then it returns the infix to prefix simplified form because it can't further evaluate it. So the prefix form is going to be the final answer of that 1 times f of x plus 0. That's just a consequence of the we are leveraging the Lisp interpreter to represent our actual um, equations when we're doing the simplification. Now, one thing that we hit last time that that we're going to be talking about today is going to be this equation here, x. Okay. Looks like that actually worked. Hold on. So we actually got the 6 times x stuff. Right. All right. So this works. Let's see, what about this other one? I don't think this commutativity one works, if I remember correctly. X times x plus x times y plus x times y plus y times y. This is a basic standard equation, but you can see that this does not actually simplify to the way we expect it to. Because of associativity rules, it actually didn't recognize that the middle two can actually be further simplified. Now, if you went ahead and did x times x plus and put this in parentheses, y plus x times y, because this will take precedence, this will end up simplifying the way we expect it to. But if you end up doing x times x plus x times y, x times y plus y times x, which again, this is just a commutativity thing that we would recognize through our own visual notation. The simplification doesn't actually occur. And the reason for that is because commutativity isn't actually complete in the implementation that we talked about. Okay. Um, the So one of the things about the implementation rules that we're going to be covering today is this associativity and commutativity. We're going to first cover this one piece here, which is what ultimately gave us this, okay, which is important. How did we apply the parentheses to the equations before we ran the simplification? And then the next thing is if we did this, what ultimately caused it. This one actually is just a direct result of applying the simplification rules here that we've done to a form that would allow evaluation of just the um, equation, the coefficients that represent this equation. So xy plus xy, so 1xy plus 1xy. And that's just a direct result of just this lookup that we have here. But this is the more important part respected to the second aspect, which is the commutativity, and the more importantly, the lookup rules for um, the creating the associativity of the equation. Okay, and so this is something that I think I'm still kind of like wrapping my head around, that I'm kind of going to be talking about today, at least from what I've understood. And then if there are questions, I can more or less try to answer them. Um, to begin with, we need to first deal with um, grouping numbers and or symbols together. Okay, and using the pattern matching infrastructure that we code, what ended up happening is if we go and look at the rules here, um, above, before these actual simplifications. Sorry, not here. I think it's below here, the is number stuff. One second. Where did this actually hit? I think this is here. That's if it's a variable. If it's a variable number, yeah, here we go. So we add first a couple rules about defining what are numbers. All right. Um, this rule ultimately is going to be leveraged to actually look up the rules on the right hand side here, and these abbreviations will then be leveraged to actually go and simplify the numerics simplifications part of the simplifier. Okay, so it essentially effectively transforms the numerics of the simplifier, right? Um, so all this is doing is saying if we're dealing with a number n and a number m and a symbol s, then we have this sort of conversion of s times n is equal to n times s. So this is actually the commutativity property of multiplication that's encoded in our search space. Okay, so here n is a number, s is a symbol, which is basically not a number, and we uh, go ahead and recognize that, okay, if we have our symbol before our number, let's just flip it. Okay. Um, we can also, I believe, change this to being something like this and add here s times s. Oh, this requires one more not a number application just so that we can do the rule. So let's call this not t, let's call this u. Okay, so we have now a u symbol that can also be treated as a symbol in this database, and we could do s times u equals u times s. And let's see if that actually extends what we need. Now, obviously, we need to reload this guy. So let's go ahead and update that following this. Right. Go here, simplifier. Well, we need to go and probably reload the simplifier. Requires Macsyma R. Loaded. Simplifier. Okay, so now let's do x times x plus x times y plus y times x plus y times y and see what happens. Oh, my apologies. I need to actually write x times x plus open parentheses x times, because this is not going to work yet. We haven't dealt with the associativity piece yet. Y times x plus y times y. Damn it. Okay, there's still one more thing we need to handle. Okay. Oh, maybe I just need to, you know what? Instead of modifying it like this, let me do this. Um, Shoot, these are all the derivation rules. And again, these are all very simple things related to uh, um, derivatives in calculus, which we'll touch base in a bit once we've actually handle the trigonometric functions too as well. But first, let's try and simplify this guy. Simplification rules. Map car. Even though we're just going to have one element here, we could add more symbolic conversions here. Simp rule. Do that. And oh wait, I'm dumb. My apologies. Do this. And append simplification rules with the okay. This, let's go ahead and get this kind of matching what we have here. Okay, and we'll have s plus u equals u plus s, which is community property of addition. And let's try s times u equals u times s. Okay. Let's try that. 2. And we don't need to necessarily call, so we could just test this here. X times x plus x times y plus y times x plus y times y. Let's see what happens. Oh, so we kind of broke it because of y. What did I do? Okay, so we're gonna have to probably do this again. So it looks like it may not work everywhere the way we expect it to. Let's see if me doing this Macsyma R will reset that. No, it didn't. Okay, hold on. Got to restart my Lisp because I kind of blew it away. Let's start this again. A lot of this development is just me extending what's currently there, but the basic idea is still fundamentally the same. You are doing a basic lookup. You are adding an additional rule. It goes and literally extracts the rule after it converts the prefix rules and that to a prefix form, and then it checks to see if we can evaluate. And if we can evaluate, it goes ahead and evaluates it. All right. So let's see here now. Um, so what did I do incorrectly here? So we do set package PAIP requires Macsyma R. Okay. And now let's call simp on. Oops. Okay, so we're back. So let's go ahead and start with the simpler one of these. Okay. Which is, instead of doing this, let's do this. Let me see if that actually will cause any issue. So it does not like the fact that we're trying to add at the end of the simplification. Let's go and do this. Let me see if it was in order, if that would actually help things. So what I mean by in order, if the ordering of the rules in the knowledge base when it looks up something will actually cause any difference. Right now, unfortunately, since I added this rule to the rule base after actually loading Maxima R, it's going to get that it's probably getting a rule that's actually taking precedence to this rule, which doesn't make any sense. So let's see if that actually will change. And if that changes, then we may have to go and actually modify the rule that I did earlier and add this symbol into there. So let's go ahead and do this. Set package PIP. Good. Requires a R. Okay. Let's run the simplifier that we ran here. And okay, so that is the problem. That is, there's one more attempt that we could do here, and then I'll just go ahead and move on, which is here and that. Oh, wait. Okay. May have to do this one more time. Load quick Lisp, set package to PAIP, then go and load Maxima. Now let's see what happens if I do this. Interesting. Why is it attempting to pattern match. If S is not a number and N is not a number, YX is okay. So the order in which matters. It's trying to simplify the expression here in stack 9. So let's just go through each of them. Rule-based translator. Attempted to do that, then maybe the base case needs to change. Let's see here. Let's do this. Because I guess it's because there are two rules here dealing with commutativity that's causing an issue, which is kind of weird because in one we're dealing with just symbols and the other one we're doing a mixture of symbols and let's do that. Let's move this up and add that this way. So we're prepending the rule rather than appending the rule. Let's see if that works. Quick load. Set package to PAIP, which allows us to use this. Okay, and that still also doesn't work. But which rule did it actually try to apply? Let's see here. In rule-based translator. Times u not a number p. So for folks who are just joining us, we're debugging this issue for actually being able to add and deal with commutativity of expressions and simplifying expressions in the current existing space. The current implementation of Macsyma dealt with some basic rules of commutativity and associativity, but did not actually handle expressions full expressions themselves. So, and I could show you some other examples. And this is basically an exercise. This is actually an exercise that's in the end of the chapter that we're basically going through. But I feel like this is something that should have been fairly straightforward to implement, just because where it's just an extension of this already applied logic of dealing with symbols, which is we have this non-number symbol S, and if we just create yet another non-number symbol U, we should be able to actually go and handle all those cases. But I guess it's probably not dealing with the simplification expression. Maybe how it's doing the lookup is not. I mean, it's the same well understood translator that we've done before, so I don't think we've changed. There was anything changed here. This is in prefix expression to prefix expression using prefix rules. That's fine. Simplification rules, we'll deal with those later on. Exponential thing. Prefix, infix, simplify. Okay, so we called simplify on the additional expressions that were provided. See, this is what I thought we would do. And then we'd call it's an atom, we'll do it. Otherwise, we'll keep on further evaluating it. And simplify expression, as we saw before, what it's doing is it's essentially calling functions or evaluating them. In this case, in case of apparently this is actually technically a known limitation. Okay, well, before I continue on debugging down this path, just one brief thing. I hope people understood that the associativity and commutativity rules that were applied here are the ones that we're actually taking a look at and we're trying to extend to handle the simplification case. Um, the rules required us to deal with numbers in particular format, in groups of two, so that way we could actually go and simplify them. This is why we have two symbols, n and m, as being numbers. This will, and again, that's only mainly because the function application that we're actually doing after we convert to prefix form is essentially taking in only two arguments, as we're going through the expression tree. Um, the first thing that we were looking at before, and I guess the easiest way to actually go and fix this is first go here. Oops, do this and abort here. Is us actually, let me go and change this guy temporarily. Get rid of that. Get rid of this for now. And we will do this, Shift G, CR. So now we've actually fixed it, and we can see that we've actually gotten what we had before. Okay, so let's just quickly review what we're doing here. Because a lot of the rules there for associativity and commutativity is basically nothing more of applying where the parentheses actually need to occur in order for a proper evaluation to happen. We need to kind of adopt some conventions when it comes to um, parenthetical application. What I mean is where do we actually go and then shift parentheses in? All right. The book mentions three specific ones that I'm just going to mention here. One is change, and that's the first rule that you see at the top there. If S is a symbol and N is a number, change X times N to N times X, or in this case, S times N to N times S. All right, where S is a symbol, which is not a number, and N is a number. The next thing we need to also deal with is combining any sort of situation where we have an outer expression that contains a number and an inner expression that contains a number to change the actual parentheses from being on the expression where you have n times s. Okay, if it's m times n times m times s, all right, where the parentheses are actually on the m times s, we actually then move it and we replace it with parentheses n times m close parentheses times s, and that's what this next rule is actually doing for us. Okay, there's all these other rules that are dealing with these variations, but effectively that's what all these are setting us up to do. We're trying to actually rewrite the equation in such a way that it can be easily evaluated. Okay, so take line 48 for example, where we have a symbol x, okay, or variable x, plus m plus n, we could just get rid of the parentheses, because of the fact that, and we can actually change the order in which those numbers are actually set up. All right. Or if we're dealing with the other option of actually dealing with changing associativity for x plus y plus n and moving it from a right associativity to a left associativity. So we always add parentheses from the left-hand side to the right-hand side for expressions. Okay. And so these are the kind of variation. The three main conventions, though, is effectively for simplifying it so that we're dealing with numbers in groups, and we can actually easily evaluate numbers. All right. Um, so the first one we covered, the second one we covered. The third one, the main one that he mentions is moving numbers out of inner expressions wherever possible. So if you have 3 times x times y, and you have uh, a number inside of a parenthetical expression, we move it to the outside. We say then n times, and then we apply it to just the symbols. All right. And so the rules there that you've encountered, that you've implemented, allows you to deal with such expressions like if we end up doing something like this, and I'm just not, I'm running the simp command directly rather than actually calling simplifier, just because it's easier rather than constantly aborting the simplifier program. But simp is basically the main function that actually gets run. So if we end up dealing with something that has 2 times x times 3 times y times 4 times z times 5 times um, and times 6, we could then see that this will actually get simplified to moving everything to the right hand side. We multiply 2 times 3 times 4 times 5 times 6, which will give us 720. And then we have x times y times z on the on the right hand side of that expression. So all that simplification can actually get done easily. But as we saw earlier, some of the more simple, obvious ones that we can normally look at, like simplifying what I showed you earlier with the x times y and the y times x, or even something even more simpler, if you just do um, x plus uh, y plus x, you could see that it doesn't recognize that you could have easily rewritten the expression as x plus y, and then you could have either written 2 times the expression x plus y, or you could have also said 2x plus 2y, because it's, and you can also see that this can handle the basic case, all right, but it's not handling these more advanced cases. And that's something that we need to go in and actually address in order for this to become more full featured and um, more robust. Okay, so this is the problem that we're looking into. Um, Before I spend the rest of the hour also digging into that problem, I want to mention that uh, the basic maxima case that we're looking at here also handles the trigonometric functions and the logarithmic functions, plus some basic calculus functions for first dimensional calculus. And that's these set of rules here. Okay, again, we go back to the logarithmic functions and stuff. They simplified it for you. It doesn't cover everything, but it covers at least some of the basic ones that we're mostly familiar with. For example, if we're dealing with um, like for the trigonometric functions, we know that For basic sine and cosine curves, we know that sine of 0 is 1, whereas sine of 0 is 0, whereas cosine of 0 is 1. Um, Sine of pi, we all know, is 0, whereas cosine of pi is minus 1. And, you know, it kind of encoded the actual sine curve and the cosine curve for the basic sine and cosine reductions that we're most familiar with. Additionally, some of the basic rules of logarithms and exponents are also written for us, so everyone can see log of e equals 1 here. The log of e to the x is equal to x, e to the log of x is equal to x, and so forth. Finally, for those of you who are remembering our trigonometric functions, we have our sine squared x plus cosine squared x equals 1 to create the roots of unity and rules for simplifying those kinds of equations. Um, some very quick examples of these that I'm gonna also briefly show is actually to me also I may as well just cover the derivations too. Additionally, the derivations are also added here. For those of you who remember your derivatives, your first dimensional differential calculus, a lot of these rules are pretty known to you. Um, uh, I don't want to cover all the specifics about how this is encoded, just mainly because I think it's fairly straightforward to look at this. Um, so, for example, this is the addition rule for differential calculus. If you have a function f and g, or in this case u and v, you have du by dx plus dv by dx. Same thing with subtraction. Um, then obviously the derivation of the negative of something is minus the derivative of the actual function itself. And then we have our product rule and the division rules that I think most of you are familiar with that I'm not going to go too much detail here. And other additional specific rules that most people should remember from basic differential calculus. The same thing here in the integration table that's provided for us too as well. So very quickly, let's just cover the three pieces here with some examples very quickly. So let's take the derivative of say 2x here, which is here. If we do simp d x plus x, and the notation that they use also, by the way, I think is important to keep in mind. Um, we have to divide, we have to actually provide the additional d in the dx here. So it's, think of this as df over dx, okay? For when you're reading this, just because um, this is what's being used by the lookup table to figure out which rule to actually apply. So in this case, ooh, wait a second, that looks wrong. Did I mess this up? Hold on one second. Let me the simplifier. Right. And KDX. That's weird. Hold on a second. That should not have occurred. Let's try this. D. Oh, right. D 2 times x plus divided by dx. That's also 0. Huh. Hold on. That does not look right. Let's do this. Let's go here, go here. Let's make sure that I didn't add any additional things here. I tried to add the rule for x times y equals y times x in the other one earlier. I forgot I added this rule myself. That's actually kind of interesting. Yeah, undo that. And the easiest way to do that, give me a second, I think is just to check out just to make sure that we have the latest. Okay, let's do a quick load PAIP here. Set package to being PAIP. Requires Macsyma R with the rules. Okay, now let's see if I do what happens. Ooh, there's still an issue. Okay, so it isn't just me. There is one thing that seems to be causing. Usually what happens, these sorts of things, it's because of the fact that somewhere, somehow I added some rule that should not have existed. Let me see something here. Okay, let's see what I did here. Okay, all right. Let's do this. Not a number does not matter, but it may. Okay, to out, then fortunately, I may have to do one more restart here. Apologize because I was messing with a lot of things a lot of times. I think I kind of messed up the actual project. So kind of resetting to what it was before very quickly. Okay. 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 Let's try dx divided by dx. Okay, good. The basic examples there, dx plus x divided by dx. 2, perfect. d2 times x divided by dx. Great. Let's try one more. Squared. This is the natural one. Divided by dx. And we get 2x. Okay, so it looks like I kind of reset everything to the way it used to be. All this is doing is honestly, if you're actually looking at these rules, is it's applying, it's doing a lookup. The approach is fundamentally the same. Okay, it takes the expression, it looks up the rules in the simplification rules. It finds the rules that best applies to this particular one. If one doesn't exist, it doesn't simplify it. If one exists, it goes ahead and runs the substitution. It goes into the right-hand side of the equation, and it goes and applies that. So in the case of the 2x, it will naturally apply, so it'll actually apply rule 82 there. Okay, u to the n, where u is a symbol or a function, and n is a number. It'll go through and actually go in and um, run that equation times du by dx. So it'll go and recursively go through each one of them. All right. So that's all of the basic stuff in a nutshell. All right. Of um, uh, maxima. Okay. Now we can clearly see here that poses some problems when we were playing around with it and we were trying to debug earlier that I think should be mentioned. Okay, the specific example that we saw earlier with x plus y plus x illustrates actually the limits of rule-based approaches because, as you can see, it's not necessarily actually doing a smart enough job to recognize the simplification rules that can be applied to actually make it easier to actually reduce this to a much more simpler form. And that's because of the fact that it's naively applying the associativity rules that are inside our rule engine. Okay, and this kind of illustrates a very important point with a lot of these rules-based approaches, and honestly, something that I think most people are familiar with, which is you could technically write all of these rules to handle these cases explicitly, but there's so many of them you may never actually encounter and implement all cases, right? Because there could be an infinite number of rules that could be introduced to handle different cases. Okay, so like in the x plus y plus x case, we have some commutativity rules, and there are different ways to actually get different answers, right? What are you considering to be reduced form is an important question. How are you handling the reduced form? How are you doing the reduction? These are all different types of rules that could be implemented, but the pattern matching language that we've been encountering right now, and the approach that we've been encountering, which is this: if this um, left hand side expression matches this rule, then go and apply the right hand side. Then you have this issue where you can't necessarily handle the case that we've just addressed because the fact that it's just doing an if then kind of approach, right? Um, and the book kind of more or less kind of iterates this quite a bit in section 8.5 about the limitations of the rule-based approaches. And I quote directly from the book for this, which is: to handle all cases, we would need an infinite number of rules. The pattern matching language is not powerful enough to express this succinctly. It might help if nested sums were unnested. Um, but once the arguments are grouped together, we could sort them. And but this approach of grouping needs to be done with care. And the example that he provides is not so much the 3x times 4x example, which can be reduced, as far as I know, but times x. Let's see here, 3 times x plus 4 times x is going to be okay. All right, so it also doesn't handle this case too. Interesting. But if it did 4, hold on, 4 times x plus 4 times x. Okay, so it's able to actually recognize some of them, but not all of them. Okay, that's right. Um, in this case here, the way we currently took the approach, all right, we would want to probably have, once 3x and 4x have been addressed, we should have actually been able to sort the same place as x and 4 times x so that they can be combined to 7 times x. But the way it currently stands is because we have this rule that we showed you earlier, specifically um, this n, not the nm case here. It's, I believe it is, no, this is n times s, n times x. So we parenthesize this n times x here, line 44, and then we added it to the another one that gets added, which is 4 times x here. But what we should have recognized is 3 times x plus 4 times x can be actually moved into the same case as 4 times x plus 4 times x, and we should be able to reduce it. But it didn't recognize that pattern, which is interesting to me because the fact that this equation here is no different than this one that we've encountered. The only difference is a 3 from a 4. So that just illustrates some of the limitations of this approach in uh, the integration stuff. I mean, sorry, in the rule-based approach. Um, Before we're going to end, I'm just going to dive a little deeper in, just because 8.6 kind of reminded me of this, which is in my notes, which is we're going to dive a little deeper into the integration piece, just because it's particularly interesting on how the integration rules are actually applied. Um, so in order for us to handle the integration and differentiation rules, um, sorry, the, when we deal with differentiation rules, there's a clearer way of actually applying the expression. But when we start dealing with integration, from the rules of applying integration are um, somewhat of a fine art, right? And remember, we're not talking about numerical integration because this is not evaluating a function with respect to a range of a to b, right? Because there are ways of computing that. Remember, uh, you have trapezoidal rule, you have midpoint rule, you have the um, the left triangle rule, if I remember correctly. Um, there's also um, there is and these are all rules of quadrature basically. There is so quadrature rule is the trapezoidal, as I mentioned. The midpoint rule is the one that I just mentioned. Um, then there is also the and these are all just integration points. You know, from if you have a rectangle, You have the left rectangle rule and the right rectangle rule, which is all about how you and these are all ways of computing the Riemann sum essentially, um, from a for a Riemann integral function. Um, so you have the left rule, the right rule, the midpoint rule, the trapezoidal rule for you have the upper Riemann sum or upper rule and lower Riemann sum for the lower rule, and these are all rules for numerical integration. Here, what we're talking about is computing a symbolic integral. And symbolic integrals are a special beast because of the fact that, remember, you are not only you are computing essentially a symbolic function, right? Where it essentially needs to apply certain rules. It doesn't actually do any sort of computation. You need to actually use some logic to actually be able to group terms and then compute the actual integral and so forth. So Dr. Norvig actually leveraged a couple of the standard techniques that most humans actually leverage from freshman calculus, and he encoded them here in the code that I'm still kind of wrapping my head around here, just mainly because I know some of the basic integral tables here, but no, this is not the integration table. This one is, hold on. So you can actually compute some of these basic integrations for um and the main technique that he implements is something he calls the derivative divides technique that um, most people in freshman calculus have covered. I don't, um, which is basically f of x dx is equal to the integral of f of x dx is equal to the integral of f of u du by dx, which makes sense for anybody who's actually, if you actually go and deal with the arithmetic, right? So to write this, I'm going to use the int notation just to give you guys this. So basically, this derivative divides rule basically says int of, I'm going to use capital INT, int to represent integral, just like Dr. Norvig is using. Okay. And the integral of f of x dx is equal to the integral of f of u du by dx. Now, for folks who are looking at this, you can clearly see this piece here, this conversion of it is pretty standard. Most people do this when they're dealing with integrals. And so that inner function is a u with respect to x, is a function of u with respect to x. And then you could compute the derivative from that and be able to compute the uh, the inner function of it, right? So an example of it is uh, applying the derivation is let's say um, so if it's x times sine x squared, we could do We just have to, substitute the functions, right? So like, let's say that we have this following function here. Um, this is the book example that he uses. So if you have example, the integral of x times sine x squared dx, if you substitute u to being x squared, then du by dx equals 2 times x, right? Which means then um, applying this rule is just substituting into the equation what we just computed, right? So so x equals, which means here x equals um, 0.5 du by dx, right? So now this will then become, the above will end up becoming the following, right? Int x times sine x squared times dx equals 0.5 times the integral, or 1/2 times the integral of sine of u, because we're substituting x for with 0.5 du by dx, all right? Sine of u times du by dx times dx, which itself is just going to equal to 0.5 times integral just do this integral of sine u du, right? So that's just simple substitution. So from basic integrals, we can actually, like, the trigonometric functions where we know what the integral is, we could just define a rule for it. And since we know that um, in this case, sine x, the integral of sine x is minus cosine x, right? We can substitute that, and then we know then that the final answer of this is basically minus so substituting the integral of sine x equals minus cosine x, we get 0.5 times integral of cosine of u, which we know that u is actually x squared, okay, and it's actually minus 0.5 because of minus cosine x, and then our final answer is just going to be cosine x squared. So this is kind of the derivatives divides in a rule in a nutshell, right? Because it's all a series of substitutions. So what we have up here in line 92 through 101 is a series of these basic lookups, right? And we could do basic integration with these um, rules. And some examples he provided here, we're just going to go through quickly here in the last 10 minutes, which is, let's take this example right here. If we run this, oh, hold on one second. I'm going to have to reduce this. Actually, why am I doing that? Continue, continue. Let's just go ahead and, instead of doing that, we don't need to comment this out. We could just apply, get this, yank it, paste and see what happens. You could see that if we run any of these integrals for the trigonometric functions where there's a direct lookup, this is actually going to give us an answer. But if we do, say, integral of just x squared, okay, and make sure that we put that, we're not going to get anything. Okay, we get x squared squared instead of 1/3 x cubed. Okay, and that's because it's just applying the rules. This is just doing a lookup. It's not doing anything um, the way we expected to. Now, um, that's kind of the way it does this is kind of interesting because inside the code, the main thing to look at is this factorize expressions, and it uses two interesting notations here. One is naturally labels, which most people should recognize now. But in case you've forgotten, labels allows us to define an inner recursive function that we could then leverage. In this case, factorization naturally being a recursive function to actually factorize any expression. We actually leverage it here to go through a given expression, and based on whether it starts with an x or whether it starts with starts with a times or divides, it actually applies particular rules in a particular way. And so this factorization piece actually goes through each of the individual expressions to reduce them to their basic factorized entities, and then it it doesn't necessarily use all the rules that we've defined in the integration table. Where that comes into play is the main integration. I think, if I remember correctly, it's in the main integration rules where it actually goes through and applies. It grabs each of the individual rules and then loads them into the has a function, a simp function to get applied later on, and that's where this comes into play. So if you look at in the integrate from table, it's grabbing the rule here, and then it just runs the substitution from the left-hand side, right-hand side of the rule. So it runs essentially the derivative, not necessarily the derivative divides rule explicitly, but it's actually applying the right-hand side of the rule into um, with the arguments in line 278. If you recall, what the substitution does is it takes the new argument. This is the old, left-hand side, and the tree that we're applying the new argument to is the right-hand side of the same rule, and then we return that. Okay. Okay. Um, and one final thing that I was going to briefly bring in. Yeah, here it is. The derivative derives rule that he actually implements is right here, and this is using two other functions, a couple of ones that I'm kind of ignoring here, one of which is not the free of, which is really a straightforward function. A free of just basically checks to see that we are dealing with an expression where we don't have any variables in it. And then we have this search function called find anywhere, that goes through and checks to see if a particular expression occurs anywhere in the given tree, and that's what's actually leveraged in integrate. Oh, I forgot that we also have this partition if function here that was defined here. Yeah. So partition if also is basically implementing partition. Um, on what it's a multi-value return. The first value is going to be the yes list, and the second value is the no list. So anything that don't elements that don't need to be applied are that don't satisfy the given predicate are in the second argument, and then the first one is just anything that satisfies the predicate. Um, with the remaining 4 minutes, I'm going to stop here. I was going to actually get a chance at trying to see if we have a time to actually go in and uh, look at that difficulty of applying the rules that we were trying to do earlier. But it looks like I'm running out of time to be able to do this. So for those of you who are still online, um, are there any questions? Okay, well, in that case, next week we're gonna probably spend a little of a coding session here and review what we've actually learned from the last couple of chapters and studying the first four systems, because I think we are at the end of part one, if I'm not mistaken. Yes, we are at the end of we're at the end of part two, and we're gonna begin a very interesting set of chapters that are mostly dealing with Lisp and efficiency, starting with chapter 9. So, um, next week is just basically a review of the search techniques that we've talked about. For those of you who haven't actually covered our previous videos, I encourage you to probably join in on us next week to actually just jumpstart your study of classic artificial intelligence, and then we could get started on some more interesting stuff. Before I let you all go, as usual, AFP is looking for people to give talks. For those of you who are interested in giving an online talk, feel free to reach out to me. I am Bugram on Slack, as well as uh, in Tech 404 and functional programming.slack, and I'm Bugram also on the Lisp Discord server. For those of you who use Discord, um, go ahead and reach out to me. Provide your talk topics, and I will make sure they get scheduled. Um, and without further ado, I hope all you have a great Monday, and I will see you later.